We are now recording. Let's go to current slide. And while we're waiting for that to open, let me go over just a couple of things on here now. If any of you are in full-term courses, which I'm guessing some of you are, but some of you probably aren't, the 60% completion date is today. I don't know if y'all realize what that means, but if you're on any type of federal financial assistance, this is for Title IV funds, it says. If you're on any type of federal assistance, if you have withdrawn from a course before today, you pay it back, okay? If you withdraw after today, these are full-term courses. The one coming up for this mini-term course will be into next month or maybe early November, but so that won't count for y'all yet. Okay, it'll be about 4 weeks into the, maybe 5 weeks into the term, mini-term. Okay, I think that's most of what I see here. The volleyball team is hosting Gadsden State tomorrow evening on the Birmingham West Campus. That's the Arthur Shores Fine Arts Building, which is also our gymnasium, and that match will be at 6 o'clock. Unfortunately, I'll be here until after 6 on this campus, so I probably won't be able to get to go to that. But we have an outstanding volleyball team, and they're doing quite well this year, so if you can get by to watch them, it's worth it. Okay. Now, other announcements that pertain just to this class. Finally, okay, I think Blackboard set up completely. Under syllabus and book information, I have the syllabus. I think I got all the corrections made, so it's out there. Under instructor information, the tab right underneath that one, the syllabus one, I have my locator card, updated, showing this class, not the first mini-term class. Okay? That's in that first group of blue tabs. In the second group of blue tabs, the one that says handouts, PPTs, and more, or something like that, PowerPoints and more. First thing on there is the link to the YouTube videos. I got that out there last week. Okay? But also in that is the research paper instructions and all the videos, the PowerPoints. So all that is there, out there on Blackboard now. If you have, yes?
No disrespect.
I'm sorry?
I said, I don't mean any disrespect, but can we get an extension on the research paper bonus for the first month? Because we just got the information on the parameters and such.
Well, they were on the YouTube videos, and I put those out last week.
YouTube video didn't come out until the end of last week.
Right. And we still got another week of October, so you got time.
Not really. I mean, I'm just saying.
Well, Okay. We can go 1 week into November for that one more bonus point, 2 bonus points. But then the rest of November will be 1 bonus point. December will be none. Okay. So it's just a point, but no problem.
That'll be what's the date? November what?
The first week in November, whatever that is. It goes from 1 to the 7th. I don't know what date the class meets, but
the last day we meet is November 7th. You know what I'm saying? So
right.
You want to end by the 7th or 8th or what?
The 7th, the 1 week into November. Because I had the video out there before the end of the first week, so I'm giving you an extra day or 2. Okay. Any other questions? All right. Oh, yes.
When you first started the class, you asked about who's graduating in December.
Yeah.
So when we take our finals, it's going to be that Tuesday or Thursday.
Okay. If you need it, well, let's see. I'll find out from them when they need the grades. Okay. Last fall, they said they didn't need them any earlier. So I imagine it'll be Thursday. unless they change it for this fall, and if they do, then you can take it whenever you need to.
Yeah, because I was probably going to take it Tuesday, because that was going to be my last day here, because I was going back home.
Well, that can be worked out as we get closer. Yeah.
Yeah, I'm in the same position as him, but I mean, we graduated 1 or 2 Friday. You know what I'm saying? And then, I mean, we won't get out of here till 7, 8 o'clock.
Right.
I'm just saying we have other things to do to prepare for the graduation, family coming in town, so on and so forth, you know.
Well, yeah. Okay. The final exam won't take you until 7:45. Okay. Yeah. If you check with the people who were here the first mini term, we were through with the final exam. Less than 30 minutes into the period. So, and we're not going to have a lab that day because it's the final exam day. So, it'll only be the very first part. Okay. All right. Any other questions? Good questions so far. Okay. And let's see whether anything else I needed to do. Oh, what's the day going to be like? Well, we're going to have class for the first 2 hours. Now, part of that is already gone. Then we'll move down the hall, same lab we were in last time. Today's lab, much shorter than last time. So you'll be able to get the lab done pretty easily, I think. And then when you finish that, you're allotted 2 hours for that because it's a 2-hour lab period, so you're allotted that. I doubt if you'll need it, but if you do, you got it. And then we'll probably come back here to the classroom the last 30 minutes, and that's when the test 1 will be. And so for test 1, you can have your formula and equation sheet. Anything you want to write on a piece of paper, you can have as notes for the test. And also, I highly recommend you have a calculator, okay? Because there will be some calculations on this one. More calculations on this test than probably any of the other tests we have. Not that many, but there will be some. And the rest of it will be fill in the blank, multiple choice. Yeah, I think that's pretty much it.
Are we having a word bank or do we get off?
It's pretty obvious type stuff. The multiple choice, you have the choices there in front of you. The others are just things that we talked about in class, and it's not any words that are hard to spell. So that's the main reason for a word bank in my mind. Okay. All right. Good questions. Any others? Okay. Where we left off last time, we were talking about forces, and a couple of different ways that we deal with forces, or forces deal with us maybe. Some are applied forces. I push on the desk, okay? That's a force, okay? Other forces are forces that happen in nature, okay? Gravity is pulling me down. That's what keeps me from floating away. When we're talking about the fundamental forces, these are the forces that happen in nature, okay? These are the most basic of all the interactions, and they're listed here from weakest to strongest, but there are some interesting parallels, contradictions you might say in it. Okay, gravitational forces. These are mass interactions. We'll see a formula a little bit later in this chapter about describing gravitational forces. They're mass interactions between any two objects that have mass. This goes from astronomical distances, like planets, stars, and galaxies. They all are affected by gravity, okay? Down to me standing here, the paper falling off the desk, things really tiny, those are affected by gravitational forces. Same rule applies for all gravitational forces. Now, like I said, this is a weak force, but as you can tell, they go long distances, okay? Gravitational forces work over very, very long distances, okay? The second of these, electromagnetic forces. Now, that sounds like two, but they really are one. Electric forces are forces between two charges. If they're unlike charges, they're attracting. If they're like charges, they're repelling, Okay? Magnetic forces are between two poles of a magnet. If they're like poles, they're repelling. If they're unlike poles, they're attracting. Gravitational forces, always attractive, never repulsive. Okay? But electromagnetic, both electric and magnetic, both repel and attract. These are charge interactions for the electric part, magnetic interactions for the magnetic part. This is described by electricity and magnetism, and the atoms and molecules, how they're held together, how things are built. Most of chemistry is defined by electromagnetic interactions. Now, why do we say this is stronger than gravitational? Yes?
Which one did you say the opposites attract?
Both electric charges, two positive charges repel, a positive and a negative attract. Two negatives repel, a negative and positive attract.
And that's both with the electric and the magnet?
And magnetic, two poles, if they're like poles, they repel, unlike poles, they attract.
The opposite.
Yeah, a north will repel a north will attract the south will attract the north, and the south will repel the south. Yeah. They both act the same. Okay? Now, why do I say these are stronger than gravitational? I don't know if you've ever seen this little demonstration. I'm not going to do it for several reasons. But if you have a rubber comb, which I don't right now, okay, and I were to comb my hair, which I don't, never mind, okay, not that funny, okay, and I had little pieces of paper here on the desk, and I comb my hair, then take the comb and lift out the electrons that I brushed off my hair onto the comb, okay, they now have a different charge from the little pieces of paper. I hold it down here, the pieces of paper go up toward the comb, okay? You can probably find that very illustration on YouTube somewhere. You'll have to figure out how to find it. But anyway, it's a very common type thing. Well, guess what? When the pieces of paper move up here, gravitational is pulling them down, the electrostatic is pulling them up. So it's the electrostatic overcomes gravity. So it is a stronger force. But its range is much shorter. Much shorter. Remember, the range of gravitational forces goes astronomical distances, literally. But the range of electromagnetic forces are much, much shorter, even though it's a stronger force. Okay? Now, as we said, atoms and molecules, what holds them together is mostly electrostatic forces. They either share electrons, exchange electrons, or something like that, and you have electrostatic forces, you have other types of bonding that happens there. Well, certainly atoms and molecules, sub-microscopic scale, okay? Really, really small scale. So that goes with large scale, about the biggest you normally see are clouds creating lightning. That's pretty big scale there, but it's nothing like you see for galaxies and planets and stars and stuff. Now, these two, not a lot of, there is a big difference, but nothing that we can describe too well here. And physicists are not really all that creative in their naming. They name them weak forces and strong forces, okay? These weak forces are much stronger electromagnetic or gravitational. They're involved in certain nuclear reactions, okay? The nuclear reaction is like you have in a power plant or an atomic bomb or something. These are the weaker of these two forces have a lot to do with that. Now, if you can imagine that, you're talking really small scale. If you're talking about between the nuclei of atoms, that's way smaller than atoms and molecules. Okay, the nucleus is really, really tiny. That's called the weak force. The strong force is inside the nucleus. Okay, especially if you think about this. Okay, what is the nucleus made up of? Anyone know? Okay, protons, which are positively charged, and neutrons, which have no charge. So here we have a whole bunch of very highly positively charged protons in an incredibly small nucleus. And no electrons in there at all. The electrons are out here flying around on the outside, way, way away from that nucleus. Why isn't the nucleus exploding? Because those positive charges are repelling each other like crazy. But the strong nuclear force way overpowers them, just like electrostatic forces overpower gravity. These are way stronger, and they hold the nucleus together. I'm not sure anyone really understands what's going on in there, because that is at such a sub microscopic scale. No one's ever observed and really been able to test it too much, but I'm sure they've got several theories of how those strong forces work. But those are incredibly strong forces. Of course, they don't last more than 10 to the minus 21 meters. I mean, very, very, very small ranges. But within that range, they're holding things very, very tightly. So those are your fundamental forces, the forces that are in nature. They act a lot like pushing on a desk or pulling on a chair or something like that, but they're inherent in nature. Okay? Now, we're moving into section 2.3. And if you recall back a few slides ago, we talked I'll get to it in a minute. Nope, this is not the slide, okay? It's in here somewhere, I'll find it. Oh, it was way back at the beginning, I remember now. Well, it's, okay. It was further back than this. Explaining emotion, okay? It's further back than this. Yeah, well, I'm not going to search any longer. Okay, but I'll remind you of what it said. It was way back. Now I've got to go through all this again. Okay. All right. We were talking about three types of motion we're going to discuss. One is horizontal motion, where gravity is no longer in the picture, not mainly. Vertical motion, where gravity is big time in the picture, and then two-dimensional motion, where we call it sometimes projectile motion, where you have both a horizontal component and a vertical component. We're going to start with the horizontal motion on land. Okay? And it doesn't have to be on land. We're going to do it on tracks. Okay? In fact, ours isn't going to be horizontal. It's going to be slightly vertical, but it's going to be one-dimensional motion. That's the key. So it doesn't have to be horizontal, one-dimensional motion. All right. Now, if you recall also what Aristotle had said, he said horizontal motion requires a force to keep an object moving. And sure, that was his observation, not tested, but just observed. And that's what this seems to be saying here. If you roll a ball on a long enough track, even a horizontal track, it's ultimately going to come to a stop. Okay? Here's the reason. If you don't have a force applied in this direction, you have some air resistance and some friction with the floor. Those two are going to ultimately stop the rolling of the ball. Will eventually stop. But you see, it's not that horizontal motion, it's that you've got these opposing forces. The net force is not zero. The applied force was zero, but the net force is in that direction. Those are the forces opposing the motion that's going to make the ball stop moving. Okay? Because you've got the force of air resistance this way, frictional force on the floor, the net force is that way because you have no Once the ball leaves your hand, you have no more applied force in that direction. Now, however, if you do have an applied force and you keep it going, and I almost want to say that it's not quite the same. Winter Olympics. Have you ever watched the curling competition? You even know what I'm talking about with curling competition? Huh? Yeah, it's incredible watching them go. They're sliding something down the ice, and that ice looks like it's perfectly slick, okay? Stones is what they're sliding across there. And they're polished stones, too. I mean, as slick as they can make them. And they're sliding this down. It's sort of like, what's the yard game that you knock the other people's things off, you know, so same type deal, okay? But they're sweeping, they're doing everything they can to keep that moving, okay? I'm sure they want to get behind it and blow on it, okay? They can't do that, I don't believe. But you see, there they've minimized the force here, the opposing force, and there's almost no frictional force between the stone and the floor. The ice is not really a floor. The applied force, they did it then. But if they could blow on it, that could be the applied force, and these would be the minimal amount of resistive force they have. You can keep it moving, it seems like, close to forever, because your net force is zero. So if the motion is there, and the net force is zero, nothing is there to change the motion. So it just keeps on trucking. Okay?
How do they store that?
How do they what?
How do they store curling? What's the object of the game?
To knock the other people's stone away and get the closest score. It's sort of like horseshoes. Yeah.
I was thinking, what he was saying, remember, the game you talking about was cornhole. Like the sandbags.
Yeah. It's a lot like that.
Yeah.
Yeah.
Knock the sandbag off, the same thing with curling. They get their other stone and knock it out of a particular area.
It's not far from horseshoes either. I mean, horseshoes, if you get so distant from the stake, you get what, 1 point. If it's a leaner, you get 2, and if it's a ringer, you get 3 or 5, or whatever it is. It's something similar to that, you know. And if you can knock the other person's horseshoe off or away, you get the point. They don't get it, that kind of stuff. But I don't know how they score curling. I don't even know how they call it a sport. But that's another issue. There is a lot of strategy to it, I'm sure, and technique and all sorts of stuff. So, natural motion question. This was the thing that Aristotle was talking about. Natural horizontal motion. He said you had to have an applied force to keep it going. That's only because there were opposing forces he did not recognize. Okay, so the question here is a continuous force needed to keep an object moving? No, not in the absence of any unbalanced retarding forces. But when do you have no unbalanced retarding forces? Hardly ever. Out there in space, basically none. So there, you're just going to keep on trucking, okay? Because there's no air resistance, no friction, nothing. So if you apply the force as motion's happening, it's going to keep motion moving. That's why it's pretty important for those astronauts when they're doing the spacewalks and repairing things and doing that kind of stuff, that they remain tethered to the mothership. Because if they weren't and happened to push away, there's no way to get back, okay? They would just keep drifting forever, okay? Scary thought, but it's sort of true. All right, another concept here, inertia. It's the measure of an object's tendency to resist changes in motion, okay? Including being at rest. Now, a lot of times if we think of something being inert, it's just sitting there. But inertia could be moving, and the tendency not to change its motion, that's inertia. Whether it's initially at rest or initially moving, that's all inertia. And there's one quantity that's very closely related to, that is mass. The mass of an object The greater the mass, the greater the inertia. Okay? I use the example of if I were to rear back and throw a ping pong ball at you as hard as I could. Odds are it wouldn't even get to you. Okay, the air resistance would be enough to keep it from it. But if I were to do the same with a bowling ball, yeah, you don't want me to do it. Okay, I don't want to do it. Hurt my arms. Okay, because its inertia, its tendency to resist changes in its motion, bowling ball would be far greater than that of the ping pong ball. Okay, because bowling ball has a lot more mass. So here's the example I was just giving. Motion continues unchanged without unbalanced forces. For instance, the satellite up there. Just going to keep moving in free space, constant velocity. You do not have to add any more forces to it. In fact, if you do add a force to it, what's going to happen? It's going to change its motion. It'll either speed up, slow down, or change direction. But if you add any other force to that, it's going to change its motion. With no forces, it's going to have constant velocity. Okay? A retarding force, a force in this direction, if it's moving this way, and you apply a force here, it's going to slow it down. It decreases its speed. If you apply the force here, push back this way, it's going to increase its speed. If you have any type of perpendicular force applied, sideways force, then it's going to make it turn, which is a change of motion, because motion deals with velocity. Velocity has direction. It's a vector quantity. Okay. So here is the retarding force. Okay. It would have to be something you applied if it's out here in space. If it was up in the higher part of our atmosphere, the air molecules are enough to be a retarding force. But if it's out in outer space, there aren't any air molecules to speak of. So any kind of retarding force, for instance, a meteor might hit it. Okay? And if it did, that's going to slow it down, and that could make it lose its orbit, unless you boosted it back to the original speed.
So in space, it's like
Say it again.
in space,
Yeah.
whenever traveling, like say a meteor or something hits it and slows it down, would it ever lose enough speed to fall out of outer space?
It certainly could. Well, yeah, to come back to Earth, to crash. Yes. It can easily happen and has happened. Usually they have boosters there, so if something were to happen like this, they can do a little bit of a boost and get it back to its original speed and direction. Otherwise, they're in trouble, in pretty serious trouble. Because a lot of those satellites, y'all heard the term geosynchronous? Okay, what that means is wherever the Earth is here, that satellite, to use your GPS, things like, GPS would be the best example I could think of. That has to be always in the same position relative to the Earth. Same position. If it stays here, the Earth is turning here, or it's moving here, the Earth turning there, it can't give you where you were. It has to be in the same position. So if it ever got hit, GPS could go down. So either they have to boost that and get it back to its geosynchronous orbit, or else it's no longer functioning as a GPS satellite. You're even better, perhaps. Any of you have any kind of disc, as in disc TV? What's the other one? Direct TV. Those big old things they used to have. They're pointing to a satellite. The satellite can't be moving around because they're fixed. Okay, so that satellite is in a stable orbit and it's not moving. So that's always pointing to that satellite. Because the Earth's spinning, it has to be spinning exactly the same place as the Earth. Okay? And if that satellite was hit by a major meteor, you may lose your signal. And temporarily out of order, they've either got to boost it, get it back, or send up another satellite. Both of them pretty expensive things. Okay? Now, if, however, it was hit from behind, or say it did slow down and then you fired a retro rocket or a rocket to boost it back. Now it's going to increase its speed back to where it was before or to a new speed. Okay? And that would be, for instance, if that satellite they sent out there to circle Mars, okay? If they said after a while, well, we want to swing around Mars a few times and take off and go to Jupiter. Well, that's a possibility. If you boost the speed, increase it, it will then leave Mars orbit. They have all sorts of incredible ways of doing that. They call it, I think, slingshot. What they do, a geosynchronous orbit is going to be perfectly circular orbit. It stays right in the same position. But what they do, they either let it get a little closer or a little further away, and then it gets in this elliptical orbit. And the elliptical orbit, it speeds up when it's close to the planet, gets slowed down when it's there, and it does this and keeps getting faster and faster until it slings it out and it leaves the planet's orbit altogether. And they use that, they use the gravity of the planet to send it to the next planet and not have to use as much fuel as if they're just breaking away. Pretty incredible how they figured out how to do that. Okay. Here is the third one. If you have an unbalanced force from either side, or even at an angle, and an angle is going to increase speed and change direction, decrease speed and change direction, but if it's right at right angles, all it does is changes motion. Okay? Changes direction of motion. A perpendicular force does not change the velocity or speed, it just changes its direction. It does change its velocity because velocity is part of it. Okay, so that was our horizontal motion. Basically, that's, even though we're not, I'm going to rename that and call it one-dimensional motion. That's what today's lab will be. We'll use stuff we did covered last Thursday and the stuff we've done today. The following objects, we're not going to have a lab specifically on this, but we will on two-dimensional motion. That's coming up in just a little bit. That will be Thursday's lab. Okay. So following object is also one-dimensional motion, but this one is in the direction or opposite the direction of gravity. Horizontal motion is perpendicular to gravity, so gravity is not changing its direction. Okay. Now, here is a simple formula that tells how far the ball has dropped. Now, this is a pool ball, okay, billiards ball. Looks like that anyway. And I don't know what was holding it in place up here. Something must have been. And then you released it, and right when you released it, how many balls do you think are in this picture? One. Well, this is a time-release photograph, okay? In other words, you've got a perfectly dark room, and you have your camera here with the aperture wide open, okay? But there's nothing hitting the film. But then you have a strobe light that's strobing, I think, every 10th of a second or 100th of a second or something like that. And this was the ball at the beginning. The next strobe, it caught it there. The next one, it caught it there, and so on. What do you notice about the ball? It's getting further apart every strobe. And the strobes are all the same time interval. So what does this mean? The distance is falling is not a linear relationship. If it was a linear relationship, the distance would be the same for every one. It's not. This is a quadratic relationship, the time squared. Okay? The longer the time, then the greater the distance. Okay? By a squared relationship. Okay? And Galileo first came up with this principle. Now, like I say, this is a simplified expression of that relationship. Now, I'm going to tell you why I say simplified. This requires that your initial position be 0. Okay? Not only that, your initial speed has to be 0, or initial velocity 0. If both of those are 0, then this works. If you had thrown the ball, then you give it an initial velocity, this formula doesn't work. You have to add something to it. If 0 had been down here, and your initial position was other than 0, this formula doesn't work. You'd have to add to it. So I'm going to give you the most generic of the equations that you can do. Very similar to this, but just a little bit different. Okay? D is equal to, now I'm just going to give the initial position to be D sub 0. Whatever that initial position was, that's where you were when time was equal to 0. Plus V0, that's your initial velocity, okay, times time plus 1/2 AT squared, where A is your acceleration, V is your velocity. Now, also I wanted to point this out to you. We went by a slide when I was looking for the other stuff. I'm going to go back to it because it's pretty important in this situation here. So hold on, here we go back in time. Okay. All right. Here we go. Uniform acceleration. That formula we had up there only is good for uniform acceleration. What do we mean by uniform? Constant acceleration. It's not constant speed, constant acceleration. That formula was good for that. The average velocity here is simply related to initial and final velocities in this case. So we'll be dealing with this formula too in the lab today. Okay? Because this one that we just had here is, both of these are based on uniform acceleration. In other words, this acceleration is a constant. Okay? Velocity is not a constant. The initial velocity was a constant, but the object is increasing in speed as it goes down, so its velocity is increasing. Okay? But the acceleration has to be constant for that formula to make sense. Okay. Now, there's another little myths, mistakes, and misunderstandings. Sometimes these are pretty lame, and this one happens to be getting close to being lame. Okay? The question is, do you get wetter if you walk or run in the rain? Okay. Now, it all depends on how you formulate your problem. If you're going to be out there for the same time, it's not going to matter. Okay? Except, if you're running, probably your front side will get wetter than the back side. Just like your windshield when you're driving gets more drops on it than the back shield. Okay? Hardly anything hits that if you're moving. Okay? But if you're going a constant distance, if you're running, you're not going to take as long to get there, so you won't get as wet. So walking, you would get more. So I'll let you read that. To me, it's, like I said, pretty much on the lame side of things. Okay. But let's move on to falling objects here. They go through a process of deriving this equation. And it's okay what they're doing. However, it's a little bit giving an excuse for why the things are here. Let me say this. The main reason they do that is how they came up with the 1/2 here. Why is there a 1/2 involved? Okay? Well, I'll tell you this. And most of the time, not all the time, most of the time, if you'll notice in this course, if your primary variable is squared, you're going to have a 2 in the denominator in front of it. Watch for that. You'll see it over and over again. There'll be at least one case where it won't be, but most of them it will be. The reason for that is remember who I said this formula came from Galileo? Who's the other guy we usually pair up with Galileo? Newton. When Newton came up with his new math called the calculus, that's where the 1/2 comes from. It's what they call an integration constant. Just like always, if your exponent is 2, your coefficient is going to have the 2 in the denominator. That's an integration coefficient. The little derivation they did here is good, it's okay, but it's not really where the 1/2 came from. But it's a good synopsis of how it could have been. Okay. So anyway, just let that rest like that. All right. Now, a few definitions here. Free fall. That's falling under the influence of gravity without air resistance. Where does that happen?
Space.
Second, space, as long as you're close enough to something to have gravity.
In a vacuum.
In a vacuum, for sure. And where would be a place that you would be close to being in a vacuum? Astronauts go there. Apollo astronauts went there. The moon, exactly. Okay? The moon has basically no atmosphere. And the classic experiment they did on the moon, the astronauts actually did this. I don't know if you've heard about it or not. He stood there in his spacesuit and everything because he didn't have, he was in a vacuum basically. Okay? He stood there with a hammer in this hand and a feather in this hand. And when he released them, they fell at the same rate. They hit the ground at the same because there was no air resistance. So, free fall on the surface of the moon, it happens. Because there you're in the presence of a gravitational field. The moon has gravity, not nearly as much as the Earth, but it does have gravity. But there you were in that situation. Okay? So that's what we mean by free fall. But we're going to use it here on the surface of the Earth. The reason we can get away with that, the air resistance is proportional to the velocity of the object. And as long as the object's going pretty slowly, there's not going to be much air resistance. It's going to be negligible. So that's what we'll count it as if it's negligible. In that case, the distance is proportional to the time squared. Remember that formula? Distance is proportional to the square of the time, not linear with time. Okay? The speed increases linearly with time. Okay? Let's go back. Well, we'll see that formula a little bit later. Okay? Well, actually, we've had it before. Remember? Velocity is equal to distance over time. Give me one of the other two formulas you can get out of that. Distance. Say again? Not times. Distance is equal to velocity times time. There it is. This says, multiply both sides by time, and you get this. Distance is proportional to the linear. It varies linearly with time. The distance with acceleration is time squared. Okay. So speed increases linearly with time. The trajectories, okay. This is a strange little statement, but I'll tell you what they mean. I bet you this picture was taken by somehow they released the ball here, and then you saw the pictures every 10th of a second, or whatever your strobe light was set for. Okay, and that's what was doing. However, if you had been standing down here and thrown the ball upward, just at the right speed, so it stopped right when it got there, this would be identical. It would be identical. Because when you throw the ball upward, it's going to slow down every 10th of a second, or whatever that interval is. Because gravity is pulling it downward, so your distance is related to the acceleration, but now the acceleration is downward, so it's going decrease according to that. So that's what they mean by up and down symmetries. It's going to have the same pattern going down as it did going up as it did going down, slowing as it goes up, speeding up as it goes down, up and down symmetries. All right? And then this is what I was saying earlier. Acceleration is the same for all objects, whether it's the feather, the bowling ball, the hammer, whatever it is, acceleration is the same for all objects. And that also comes from your fact that we're saying the acceleration is uniform. Uniform acceleration meaning constant acceleration. Same for all objects. Okay. I think I'm going to need to erase. Oh, there's that formula again. And you see here, the distance increases with the square of the time here. And speed, I'm sorry, I wrote the wrong one down. Sorry. Let me erase those. The one I meant to write down was this one. Almost the same one, but I just wrote the wrong one down. Remember, acceleration is change of velocity over change of time. So multiply both sides by time, and you get velocity is equal to acceleration times time. So speed increases linearly with time. This is time to the first power, this is time to the second power. Distance, in falling objects, distance increases according to the square of the time, velocity increases according to linearly with time. It's always increasing as it goes down, but it's at a constant rate. The distance is not at a constant rate, it's at an accelerated rate because of acceleration. All right, this is where I thought we were going next. Let me erase my writing so you can see this better. Now this is the distance that's falling. Now again, make your thing. Here is your zero position, top of the building. You're dropping something from there, okay? You're not throwing it, you're dropping it. When you drop it, your initial velocity is zero. If you throw it, your initial velocity is not zero. It could be positive if you threw it upward, negative if you threw it downward. If you drop it, the initial velocity is zero. And according to this formula, after 1 second, your distance that has fallen is 1/2. Now, the A here is your acceleration due to gravity. Okay? I was thinking of changing that in the earlier one. But your A here, and we have a symbol for it to show that it's not just any old acceleration. This is acceleration due to gravity. We usually give it the symbol G. And that G is in the metric units, meters, seconds, and the metric distance, then this is 9.8 meters per second squared. That's an acceleration, 9.8 meters per second squared. If you did this in the U.S. customary measurements, then you would have the distance would be in feet, time would be in seconds, then your acceleration, or G in the U.S. customary, would be 32 feet per second squared. And if you think about it, a meter is a little bit longer than a yard. A yard is this, a meter is this. So if it's 9.8 meters per second, then this is a little bit greater than 3 times that. And sure enough it is. That's close to 10, this is a little bit greater than 30. So yeah, that's 32 feet per second squared. That's the acceleration due to gravity in the U.S. customary. But notice what is happening here. After 1 second, 1 squared is 1. 1/2 of 9.8 is 4.9 times 1. So that's why it fell 4.9 meters in that first second. The second, or after 2 seconds, it has fallen. Your time is now 2. 2 squared is 4. 4 times 4.9, 1/2 of 9.8. That's 19.6 meters. So it fell almost 4 times further in the in 2 seconds than it did in 1 second. Okay, it fell another 15% 15 meters, so it was about 3 times what this was. Okay? In the next second, look how far it fell. And this is why the ping pool balls were getting further apart, because in another second, now it's 3 squared, that's 9 times 4.9, and that would be right around 44.1 meters. Is how far it fell after 3 seconds. After 4 seconds, 78.4 meters. Okay. Now, this is only distance. Notice the distance is increasing each second, pretty significantly different. And that's why I've only been there once, but New York City once. My wife's brother and his family love to go and see Broadway shows in New York City. That's an awfully expensive deal for me, okay? But we went with them one, it was in Christmas season. And of course, while we were there, we went to top of the Empire State Building, okay? And they do have all warnings all over the place. Do not throw things off the top of the building. People, I think, originally liked to throw a penny off, you know, because guess what? With it picking up speed like this, as tall as the Empire State Building, it's going to be a lot of seconds before it hits the ground. You could literally crack someone's skull. I've heard it said anyway. I don't know if it's absolutely true with a penny if you threw it off there. So, and you can do pretty much damage to a car or anything else, because the velocity by the time it reaches the ground level pretty high. You don't want to be doing it. Okay? Because what is acceleration? Change of velocity. Now, in reality though, remember I said the reason we say free fall is without air resistance, because at low speeds the air resistance is negligible. But at higher speeds, like you would get dropping a penny or something else off the Empire State Building, the speed's going to be so great now you start getting air resistance. So it's not going to be as bad as it would seem, because it's no longer free fall. Okay? In fact, it never was, but it doesn't even act like free fall. All right, now here are the speeds. Remember, it said speed increases linearly with time. So after 1 second, because your formula is V final is equal to A times T. Well, actually it was delta V, remember? But the initial velocity is 0 because you dropped it. So now you just have V final is equal to acceleration times time. That A is your G, which is 9.8 meters per second squared. Here it would be 1. So 9.8 times 1 is 9.8. 9.8 times 2, that would be 19.6. Exactly twice as fast. Exactly 3 times as fast. Exactly 4 times as fast. Now, at some point here, you're getting enough velocity, you are going to encounter some air resistance. Still not going to be too major here. But that's not the Empire State Building. Okay, so you will start experiencing more when you're up that high.
So, if someone was to like throw a baseball from off the top,
Yeah.
since you're throwing something that's starting with velocity,
Right.
it's still going to pick up velocity going down.
Absolutely. Gravity is still going to be acting on it, whether you had initial velocity, you dropped it, or you threw it. The thing is, when you throw it, your initial velocity is greater, so now it's going to still increase at this same rate. 9.8 meters per second is the increase every second. So if you gave it an initial velocity of 10 meters per second, after 1 second it would be 19.8. Here it would be 29.6. Here it would be 39.4. Here it would be 49.2, because that initial velocity would still be contributing. And the change of velocity is going to be 9.8 meters per second every second. So yeah, it carries through. So it would be even faster if you threw it off there. Now, this is sort of maybe a little hard to believe. What if you threw it upward there? It would, but see, it's slowing down only when it goes to the top. So when it reaches that highest point, wherever that is, depending on how hard you threw it, then it's going to start coming down, but picking up speed at the same rate. Remember what we said before? Trajectories exhibit up and down symmetries. So the same speed you threw it up here, on the way down, it had picked up that same speed. Because it lost that speed going up, going to gain it coming back down. So that is going to still, if you threw it up at 10 meters per second, it's going, when it gets back down here, it's going to be 10 meters per second down. Up and down symmetry. So it'd be just like if you threw it down. It just takes a little longer to get there because you have to go up and then down. But it's still going to have the same speed at the bottom. That's why, this is a pretty gruesome example, but it's true. Especially, I would hope, in third world countries you might see this. Hopefully we don't do it much here. I bet you some people do. When they go out celebrating something, firing something into the air. Okay? Not a good idea. Say again? It's got to come down, and when it comes down, all of it's going to be at the same speed as when you fire it. Okay? So if you were to fire something straight up, absolutely straight up, then it's going to go up, slowing speed all the way, and it's going to go pretty far up there. But at some point, it will stop, and then it starts falling down, picking up speed at the same rate it was losing it going up. So when it gets back, if you hit it straight up and you're still standing in the same spot, just like doing that. Okay? Almost. There is some air resistance because those bullets go really fast. So you can't discount air resistance, but it's close enough that you don't want to do it.
How many people die a year? How about my friends talk about me that all year round?
What's that again?
How many people die a year? Like around my house, it's like we got a big Hispanic population around the house. That's one of their celebration things. They go up there with guns and shoot them all around.
With live ammunition?
Yeah, well, I mean,
Well,
they're not very smart.
There's plenty of smart and not smart people in just about every demographic. I'll put it that way. But if you're out in the countryside, the odds are it's not going to hit anything. But if you're in a crowded place, it could. Now, actually, this did occur. We heard it on the news. We hadn't moved into Birmingham more than a few months when we heard it was some guy and his wife were driving down the interstate, I think somewhere east of here, I-20 east, and they had the kid in the club tail part in the seat back there, in the seat, and they heard something but didn't know what it was. They looked and the kid seemed to be asleep. And when they stopped for gas or something, went to get the kid out, holding the back of his head. The kid was dead. Because someone had been target shooting, hunting, I don't know what they've been doing, but the bullet, random as all get out, happened to hit right there. And they didn't burn. They probably weren't even inside. But it just happened to be, however, wherever they shot it, came down and was still almost as close as it was. So it can happen. So it's still not a smart thing to do, even if you're not in a crowded situation. That was so freaky. We could not believe that it happened, but it does happen. All right. Now, before we leave this page, there is a blurb at the top of the page, and this is talking about bicycle racers. But any kind of racing, this pertains. If you watch, I think this is Summer Olympics when they do the bicycle racing, and you'll see all this jockeying for position. No one wants to be in front to begin with, and they're always trying to get behind somebody else. But sure enough, that happens. And I think we talked about it before. Car racing, horse racing, bicycle racing, running. You'll see for the distance run now, if it's a 100-yard dash or a 100-meter dash, they're running as fast as they can. No one's going to drag on anyone on that. You lose the race, okay? But for long distance running, you start this way, okay? you start trying to get behind someone and drag on. Okay? Not drag racing, but the other kind of dragging. So they're talking about that there. That is definitely not free fall. Okay? It's not even falling, but air resistance is a big part of it. There's also a closer look on the next page, page 38, about free fall. So I'll let you read that. That's a pretty good blurb, well worth the read. In fact, most of the closer looks are very much worth the read. Okay. Now, also on page 38, we hit the next example. So let's see. Good place to do it. Example 2.7. A rock that is dropped. You see that word, and what does that mean?
It started at 0.
Second?
It started at 0.
Yes, initial velocity. I like I. The book uses O a lot, but I like I. Initial velocity is equal to 0. If something's dropped, initial velocity is 0. Okay? Into a well, hits the water in 3 seconds. So what's that a measure of? Time. There's your time. 3 seconds. Okay? Oh, that's a 3.0 second. That just means 2 significant digits here. Okay? Ignoring air resistance, which is probably okay to do, how far is it to the water? What formula do you think we might use? D is equal to? Second? Here it is. 1/2 AT squared, where the A is our G. Okay? 1/2. I'm going to go and write it GT squared. Now, I made a mark on the other screen. Let me get rid of it here. Okay? So, D is equal to, now, what units do you want to be in? SI or US customary? Second? US? So what is G in US customary? It's 32 feet per second squared. Always give a unit with it. Times 3, that's your time. So it'd be 3.0 seconds squared. So this will be, I'm going to go and take half of 32 so I can get rid of the fraction. 16 feet per second squared times, what's 3 squared? 9.0 seconds squared. You square the number, you also square the unit. Okay? The second squareds cancel out, and this is 44 feet. That's how, is that right? No. 9 and 4. Oh, sorry about that. I hit the wrong key. Okay. 9 and 4 is 134 feet. Yeah. Right. 9 and 4, yeah. 144 feet, approximately. Now, if you used SI units, like the book did, what would be the difference there? 9.8 meters per second squared times 9. I can't write my units in there. This will be 4.9 meters per second squared times 9.0 seconds squared. Squeeze them in there. And that would be 81, 36 and 8, 44.1, boy. 44.1 meters, okay? But, okay, you only have 2 digits here, 2 digits here, so you can't use the 0.1. That's approximately 44 meters. Okay, now how far is that? 44 meters. Right about half a football field down, okay? The well is down. And that, sure enough, is what we've got here. The football field is 300 feet, 100 yards, 300 feet, so it's awfully close. Half of a football field down. It's pretty deep. I don't want to go down there. Okay. Now, that's why they round to 44. And actually, if we had been doing it correctly here, using only 2 digits, because that's all we had, we would say this is about 140 feet. Because you really only have 2 significant digits. You can't support 3 digits. You don't have enough precision. So you would say about 140 feet. Okay. Okay. They have a second solution of how to do it. It sure is a lot more steps. I like this one better. You can certainly use the other one if you like. Okay. Now, that was it for falling objects. Okay, we've just gone past 1¼ hour, or approximately that. Now we're moving to compound motion. Okay? Compound motion means more than one dimension. Remember, horizontal motion was one dimension this way, vertical motion was one dimension this way. What we're going to be doing in labs is one dimension up and down a ramp or down a ramp. That's still one-dimensional motion. This is compound motion that has involved, well, there's 3 types of motion they're saying. Vertical motion, like we just were doing, free fall. Horizontal motion, okay, or a combination of 1 and 2, vertical and horizontal, and that's called compound motion. Another name for it is projectile motion. You don't want to shoot a projectile straight up because it's oddly going to come right back down on you. Not if you're in warfare or something like that. Not a good idea to fire the thing straight up and then hit a hole in your ship. Don't want to do that, okay? So most of the time, projectiles are fired at an angle, okay? And that's an object is in. Now, my younger brother had 2 girls and a boy. Okay, the boy was the youngest. He liked sports. The girls didn't. So when he went out to play football, what he would do was throw the ball into the air and run and try to catch it. Okay? Had to throw it really high and run really fast and try to catch it. So he was doing projectile motion. Now, of course, if he threw it straight up, he just had to stand there and catch it. So he threw it with a little bit of an angle and then would try to run. I always got sort of tickled at him watching him try to play football by himself. But poor guy. We lived way out in the country. There weren't any other kids around. Okay. So an object thrown into the air most of the time, basketball, footballs, golf balls, tennis balls, all these things are something that's being launched into the air. One exception to that in basketball, a dunk is only going vertical. Okay, that's all. Okay, but the rest of them are always thrown into the air. Here are some basic observations. Gravity acts all the time. There's never a time when gravity isn't acting on it. On its way up, gravity is pulling it down. On the way down, gravity is pulling it down. Gravity is acting always. The acceleration due to gravity, and that now they finally introduce the symbol G, meaning acceleration due to gravity, is independent of the object's motion. Whether the object is going up, going straight, going down, whatever angle it is, the acceleration due to gravity is independent of the object's motion. It always acts toward the center of the earth. Okay? So those are basic observations. There's a couple more we'll get to a little bit later. Those will do for right now. So, here's what we're talking about. Projectile motion, if you did do a perfectly vertical projectile, usually not a good idea, unless you're just throwing something into the air to catch it. As it's going up, it's slowing down. As it goes up, somewhere when it finally runs out of velocity, it stops. Momentarily, but it does stop, and then starts coming down, and it accelerates and speeds up, coming down. So slowing going up, stopping at the top, speeding up, coming down. Gravity is always acting on it. The force of gravity, and I wish they would have said the acceleration of gravity, acts downward throughout the motion. We've already said that. Horizontal projectiles. Have you ever seen those quarterbacks that try to throw the what they call clothesline type passes? They do it. The guy probably is going to have to dig it out of the ground, or maybe not get it out of the ground, because guess what? Gravity is always acting on it. Okay? Horizontal velocity remains the same. It doesn't ever change, because the acceleration due to gravity does not change the velocity in the perpendicular direction. It has no effect on it. But when you take it with the vertical motion, in other words, gravity is still pulling down, even though you throw it horizontally, it's going to dip down. Now, have any of you followed or studied or read about, what do they call those sharpshooters that fire from long, long distances away? Snipers. Okay? If you're a sniper, you have to take into account the fact that the bullet is going to be dropping the whole time. So you always aim a little bit high in order to get whatever you're going at. Okay?
Taking into consideration temperature, wind, all
Second?
I said they take into consideration temperature, time of day, wind, everything.
Everything. Okay? There's also a thing we'll talk about maybe a little bit later called Coriolis force. That's the spinning of the earth. They have to take that into account too. Bombardiers on airplanes. Or, guy for the first mini term sat right about where you're sitting. He was a fire control technician in the Navy. When they're doing their computers, they have to allot for the spinning of the earth. Now, it's not a big change, but there's a little bit. If you're firing something a long distance away, like an intercontinental ballistic missile, you have to take into account the motion of the earth, because things are going to change ever so slightly. They're going to change while that's in the air. Okay? Bombs falling from high distances are going to change. Okay? So everything is following a curved path. How you know it's a curved path? Remember that? Square, quadratic, that forms a parabola. Everything follows a parabola. Free throw, a jump shot, a golf ball, football, even tennis balls, even though they look like they're going straight up, they're always dropping. Baseball, always dropping. In fact, that's part of what makes a curveball, because it's thrown at a slower speed, and therefore there's going to be more drop to it than a fastball, which is going to take as long to get there, but it's not going to drop as far because the initial velocity was slower, so the initial velocity remains the same, but the vertical part curves it. That's part of it. I don't think they figured out what all of it is, but that's it. Now this you might find hard to believe, but it's absolutely true. If the gal up here is with her bow and arrow, firing the arrow perfectly horizontal, not allowing for any drop at all, perfectly horizontal. Okay? And the guy standing next to her, as soon as she releases her arrow, he releases his, and he just stops. They're going to hit the ground at the same time. Because gravity is acting on both of them exactly the same. Hers is going to be way down there. His is going to be right here, but still they're hitting the ground at the same time. If she's firing perfectly horizontally and they release it immediately at the same time, the component downward. Horizontal component doesn't change. That's it here, that's it here, that's it here. horizontal component does not change, okay? But the vertical component of velocity, small, it's 0 to begin with, small here, bigger here, bigger here, same difference here. They get the ground at the same time. If it's fired absolutely horizontal. Now, another sort of strange application of that, if someone were releasing something, your target, as you fired it, I wouldn't be the person releasing it, someone firing at it, but released it, then you aim right for it because they're both going down at the same speed. You don't allow any adjustment in altitude. Strange but true. Okay. Now, passing a football, same deal. The only force acting. Now, sure, when you're throwing a football, you're adding force to it as long as it's touching your hand. As long as you got it. As soon as it leaves your hand, you can't exert any more force on it. It's now only under the force due to gravity. Now there's air resistance. Okay, of course there is. What is it about the football that minimizes the air resistance? Okay. And what else do you have? Spin. Okay. You always have that. And if that ball is a nice tight spiral, minimizes the air resistance. Okay. We were at the UAB football game last Saturday. Good game. It was cold and wet, but it was a good game. I only stayed through halftime. It was that cold and wet. But UAB didn't punt often because they were doing pretty well offensively. Boy, they had this one punt. I mean, the punt was a perfect spiral. And I mean, that ball took off. It just kept going because it was spinning. Now, that also is what's happening with a rifle. What does it mean? What is rifle?
Rifling is in the barrel. Yeah, grooves cut in it.
Very minor little grooves that do this kind of twisting motion.
And they don't spin very fast. I mean, it's like maybe a three-quarter revolution the whole barrel.
Right. Okay. But what it does, it gets it spinning. That keeps it
accurate.
Yeah.
Because what it did, they shooting in, it would be inaccurate. That's why they make it like that.
Okay. Any of you baseball aficionados? What is the toughest ball to hit?
I could never get a curveball.
Curveball? A lot of people say there's one even tougher than that, and it's even slower than that.
Knuckleball.
A knuckleball. Okay? And the reason for that, there's no spinning on a knuckleball. A good knuckleball is just coming, and then anything in the air is making it go, and it's not following any set pattern. It's weird. I don't know how that works. But you know, everything else has spin to it, and that's the thing. A shotgun, when you shoot it, there's no rifling in that, and things just spread out and go. Okay, but that's all you want out of a shotgun, short range, that kind of stuff. But rifle, you want it to be good for a long distance, and that's why they have the rifling in there to get that tight spiral. Okay, that you've got going. Okay. But that's all beside the point. Okay. The only force acting on when you pass a football is gravity that's pulling it down. The vertical velocity decreases. If you throw it, and of course you would throw the ball up into the air at some angle, and when you do, its vertical velocity is going to start decreasing because it reaches a point somewhere up here, and then it's going to start increasing coming down. So vertical velocity decreases, then stops, and then increases on the way down. The horizontal motion is uniform. It does not change. Horizontal velocity does not change. The combination of these two motions produces what we call a parabola, a parabolic arc there. And that's what you got. It's what you got with free throws, jump shots. Everything else follows that parabolic arc. Okay? vertical velocity, he's given it some velocity here. It's decreasing until it stops. Here the vertical velocity is 0. Now the vertical velocity, gravity is in. See, gravity is always downward, and it's slowing the vertical velocity, decreasing it here, stops it, and then instantaneously, and then starts increasing at the same rate it was decreasing here, it's increasing here. That's what makes the parabola the parabola. Horizontal component never changes. That's why the receiver can go out there and run under the ball. Okay. I think we beat that to death. All right. Okay. Now, what we just went over, compound motion, that's going to be Thursday's lab. Okay? And we'll go down, we won't go to 253, we'll go to 252 across the hall from that on Thursday. There's a reason for that, and you'll see it once we get in there. Okay? Now we're moving into, that was all describing motion pretty much, though that was some explaining. But here's the big explanation, the 3 laws of motion. First detailed by Sir Isaac Newton. Okay? There were the approximate dates, these were the dates of his life. Galileo died either 1564 or 1563, right around the same year, within a year of the time that Newton was born. So they never met, but Newton read about Galileo. Okay, Galileo actually came up pretty much with the first law of motion, though he didn't call it that. Newton refined it somewhat, and so it's attributed to Newton, but he got most of it from Galileo, from his writings. Now, Newton, at the same time he was doing these 3 laws of motion, he had developed a whole new mathematics to really do it justice. Okay? And he had to come up with a law of gravitation to explain why things fell. And sometime either before or after, I think it was afterwards, he came up with a theory on light. Boy, this guy did a lot. Okay. But the essential idea here for the 3 laws of motion are forces. All depends on what's happening with the forces. Okay, and you'll see that as we talk about these 3 laws. Okay? Newton's first law of motion. And this is often called the law of inertia. Okay? First law of motion. Now here's one description of it. This isn't exactly probably like he wrote it, but pretty good description. Every object retains its state of rest or its state of uniform straight line motion unless it's acted on by an unbalanced force. If it is acted on by an unbalanced force, then it doesn't retain that same state of rest or state of motion, uniform straight line motion. Inertia is the thing that resists any change of motion, so that's why it's called the law of inertia, because it's maintaining its state of rest, its state of uniform straight line motion, unless it's acted on by an unbalanced force. Now, we've talked about some of those unbalanced forces. For instance, you roll a bowling ball down the lane, okay? Now, you may think it's hitting those balls at the same speed that you released it. Probably not. There is always some air resistance. But because the ball's rolling, it doesn't have quite as much, it's not quite the same as a spiral, or you're rifling on a barrel, but you still is minimizing a little bit of that. But the other thing is, if you were sliding it down the lane, yeah, it's going to have a lot of friction there. But when it's rolling, the friction is minimized. Okay? But it's always losing some speed. Not much, but a little bit. How do you know it's losing speed? Can you hear that ball when it's rolling? Sure you can. Well, if it's hearing it, that means there's vibrations. The vibrations are causing sound waves. If there weren't any vibrations, there wouldn't be any sound waves. So if you're hearing it, it's losing some energy. Okay? We're not talking about energy yet, but it's so inertia, law of inertia. Now, I won't get into it. So that's the first law of motion. Now, we're going to do several things with this first law of motion before we get, whoa, maybe we're not. Okay. Ah, here we go. I bet you most of you have experienced this before. I think we talked about this earlier earlier in the chapter. If the bus was originally at rest and you're just standing there, you're not hanging onto a strap, you're not hanging onto a pole or anything, but you're just there. Now, I don't want to say a bus. I want to say, any of you been to Atlanta Airport? Okay. Have you been in the trains that get you between those? That's worse than a bus. When they take off, they take off. If you're not hanging on to something, you're falling into somebody, I guarantee it, okay? So, if it's initially at rest, and it takes off and goes, you feel like you're thrown backwards, aren't you? Are you really thrown backwards? No. What is happening, the bus is moving out from under you. Your inertia tries to keep you right there, and therefore you fall backwards. That's what's happening. Any of you have a pickup truck? Okay. Ever had anything on the back you get chopped well, and you take off, wham into the tailgate. You stop, wham into the cab. You know, you turn, wham into the side, one way or another. Okay. That's inertia. The object is trying to stay right where it is, but the truck is either pulling out from under it, stopping it, trying to maintain its state of motion, or when you turn, it's trying to keep going in straight line motion. That's exactly what it is, uniform straight line motion. So the person feels like he's falling back, actually the bus is moving up. He's trying to stay in the same place, okay? Unless he's supported or holding on to something, okay? All right. Same thing about straight line motion. As long as it's moving in a straight line motion, you hardly notice it's moving. Maybe the vibrations, other things you might, are looking out the window. But sometimes you just can't even tell if it's a nice, smooth ride. Okay? Because you and the bus are going along together. But if that bus turns, wham, you're thrown into the, no, you're not thrown into the side. The bus cut in front of you. You are trying to maintain straight line motion. But the bus turned and you didn't want to. That's why it feels like you're thrown into the side. If you've been in the airport in Atlanta, I take it you've probably been on a flight before. Now, when you're on that flight, I bet you there were sometimes you're probably going about 500 miles per hour. Did you feel like you were going 500 miles per hour? No, because you're maintaining your state of mind. Your inertia is right with the plane. Until you get turbulence. And that's when things get really bad. Because the plane does something and you're thrown the other way. Because you're trying to maintain your state of motion, and the plane, because of the turbulence, it does something different. Okay? So Newton's first law, everything, every object is trying to maintain its state of inertia. Whether it's at rest or moving, and if it's moving, it's trying to maintain straight line, constant speed, motion. Okay? Now, the second law. Here's one shorthand way of saying it. Forces cause acceleration. Notice what we said here. Unless it's acted on by an unbalanced force. So the second law says if there is an unbalanced force, if you have a net force acting on the object, it's going to accelerate it. It'll either speed it up, slow it down, or change its direction. An unbalanced force will cause an acceleration. Now, the units for a force named after Sir Isaac Newton. Let's see what they really are. Maybe it's going to show us here. Yeah, there it is. The net force acting on an object That's the sum total of all the forces acting on the object is the product of its mass times its acceleration. Now, what was the unit for mass? Unit for mass. Anyone remember? Only SI we ever use it. We don't use it much in U.S. customary. What unit for mass? Kilogram. You got it. Okay. What about acceleration? What were the units for acceleration? Yeah, so it had a meter in it because you were moving. Say again? Per second, or per second squared. That's exactly what a mass times acceleration is. And that's exactly what a Newton is. A kilogram meter per second squared. These are your basic units. You can't get any more fundamental than that. Mass, distance, and time. Newton is a combination of those in that order. Okay? So yeah, that's what a Newton is. Kilogram meter per second squared. Hang on to that concept. You'll use it the rest of the term. Okay. Now, here's what the deal is. Forces cause acceleration. If something is accelerating, it has to have a force causing it. The acceleration is proportional to the force, or the force is proportional to the acceleration. Remember our proportionality constant? Equals m. The mass is the proportionality constant. That is the mass. And what concept from the last slide did I say mass was related to? Inertia. Oh, the 10 o'clock scholar. Okay. Good deal. Mine's here. Okay. So now we're only missing Amanda, Latricia, and Mendez. Okay. Poor Diamond's having to hold it up for her whole gender here. Okay. So, your proportionality constant is your mass. Now, what does this mean? The more force you applied, the greater you accelerate. Or, the more you accelerate, the more force is required to create acceleration. Or, on the other hand, if it's a constant force and you have more mass, what happens to your acceleration? It goes down. These are inversely proportional. Okay? So, more mass, less acceleration. They do give an example of that, and they don't do a really great job with it, but let's take a look at it. Oh, they didn't show it. They're going to show it later, so I'll point it out to you when we get there. Okay. Oh, here it is. Here it's coming. If the guy is tooling along here on his bicycle and he's applying a certain force and he's going at a constant speed, then there must be an equal and opposite force against him. We'll call that the force of the friction on the road and also some air resistance on his body and stuff, especially if he's sitting up like that. These two add up to that, so the net applied force is 0, so his acceleration is, if the applied force is 0, his acceleration is 0 because it's mass times acceleration. How about his speed? It is a constant. You're absolutely right because there is no acceleration. So you have a constant velocity. There, you're reading it right there, weren't you? Okay. No, I know, I'm just kidding. Okay. So the focus here is on the net force, how much he's applying to this. Okay? You have some air resistance and tire friction. They match his applied force, so his acceleration is 0. Okay. Now, what if they don't show it? Let me see if I can find it. I think they show up somewhere else. No, they don't. Okay. All right. In the book, it's here. Okay. He does the same thing on this bicycle built for 2. Same guy, same net force, everything. Maybe the bicycle's a little heavier or something, but not too much. But then his girlfriend sits on. Well, guess what? Look at her feet. She's not pedaling. She's just riding, okay? She's happy about it too. If he's doing the same force, what happened to his acceleration? If she had the same mass as him, which she hopes not, but it slowed down. In fact, it's cut in half if she has the same mass he did, because it's proportional to the mass. Now, let me give you this example. I may have given it before, but let me just do it again in case y'all are paying attention or not. What if you're in the aircraft traveling at 500 miles per hour, straight level flight? What's the net force on the plane? You're traveling 500 miles per hour, straight level flight. What's the net force on the plane? 0. Why? You're not accelerating. Okay, your net force must be 0 because your acceleration is 0. Because your speed was constant, just like we had here. Constant velocity, no acceleration. Right? Now, does that mean there's no forces acting on the plane? Of course there's forces acting on the plane. What's what? Gravity's pulling downward. The lift of the wing, we talked about that before, right? Bernoulli's force, that's what's giving you the lift. So those exactly balance each other out. Those engines are still firing up, like crazy, because you're hitting a lot of air resistance. At 500 miles per hour, you're hitting a lot of air resistance. Even though the plane is pretty aerodynamic, okay, you're still hitting air resistance. 500 miles per hour for certain you are, but that's why the engines have to keep firing. If they quit firing, that reminds me of the dumb joke. It was a transatlantic flight, and they were in this plane and it had 4 big old heavy strong engines on it. And they took off and just got slight wave over the Atlantic, going out there, and one of the engines died. And the guy came, I'm sorry, back it up. He said, welcome aboard everybody. This is before this happened. We've got a 6-hour flight, everything should be fine, the weather looks good, we got a little bit of tailwind, we may get there a little bit less than 6 hours, but we should be doing fine. Sit back and enjoy your flight. And about an hour into the flight, one of the engines goes out. Well, they're too far to turn around and say, hey, don't worry folks, I know you saw that, and it seemed pretty bad, but this plane is well designed, it can maintain and continue flying on 3 engines. It's just going to take us a little longer. So it'll now be 7 hours before we get there. Okay, because we're going to have to drop our speed. Okay, well, in about another hour, another engine goes down. He said, well, hey, don't worry. This plane was designed well. It can keep going. We just can't go as fast. So now it's going to take us 8 more hours to get there. Well, after a while, another hour passed, another engine. Came on and said, hey, don't sweat it. This plane was designed to go on only 1 engine. We just can't maintain the same speed, but it'll take us 9 hours from now to get there. One passenger looked to the other and said, I sure hope that other engine doesn't go out, we'll be up here all day. Okay. Done. Okay. All right. So, net force, this is Newton's second law. And Newton's second law is best represented by this equation. Where was it? Right here. F equal ma. That's Newton's second law equation. If there's a net force acting, it's going to accelerate. First law, if there's no unbalanced forces, the net force is 0, then it's constant velocity, 0 acceleration. Okay? If there is acceleration, you got to have a net force. Okay? All right. Now we get to another issue. Okay, wait a minute. Okay, wait. before we get to that issue, let's do examples 2.8 and 2.9. Okay, this may be all we got time for. Example 2.8. A 60 kilogram bicycle and rider. Okay, what's 60 kilograms a measure of? That's the mass, 60 kilograms. That's the bicycle and rider. Accelerates at 0.5 meters per second squared. Is that a good unit for acceleration? Yes, very good. Meters per second squared. Okay. How much extra force was applied to create that acceleration? So what net force did you need? Anybody? Yeah. Mass times acceleration, which is 60 kilograms, times 0.5 meters per second squared. And that gave you what, you say? 30 what? Yeah, kilogram, meter per second squared. And remember, that is 30 newtons. Perfect. Okay? 30 newtons. Extra force of 30 newtons. If you're going to accelerate, and you know this is true if you've ever ridden a bicycle, when you're just sort of going along at a constant speed, you have to pedal some because air resistance and stuff like this. But if you're trying to accelerate, you're going to have to pedal harder. You're going to have to give it more force. Same thing in your car. If you're going along at fairly close to a constant speed, you're not having to give it lots of gas, so you're getting your best gas mileage that way because you're not really good. But if you're going to then go past somebody, you got to give it some more force to give it more acceleration. Okay? Now, let's do 2.9. What is the acceleration? This time we're looking for acceleration. They didn't give it to us. Of a 20 kilogram cart. What's that a measure of? That's the mass. 20 kilogram is the cart. That's the mass of the cart. If the net force on it is 40 newtons. So your net force is 40 newtons. Well, what is a newton? What units are newtons? Kilogram, meter per second squared. Okay, keep up with those. Okay, what formula relates these? F equal ma, net force equal mass times acceleration. But this time we're looking for acceleration, so what could we do? Second? Not multiply. Divide by mass. Divide both sides by mass. That gets rid of mass here. And you get acceleration be net force, which is 40. I'm going to put the basic units here. Kilogram meters per second squared divided by 20 kilograms. That's the mass. Kilograms go out, and what are you left with? What are you left with? 2 meters per second squared. That doesn't sound like a lot, but I guarantee you're not going to be able to maintain that acceleration for long because that's going to be picking up speed pretty quickly. So that'd be 2 meters per second squared. Okay, good deal. Now, they have a little description of a second law experiment. That's pretty reasonable. We've done something like that in lab before. I don't do it anymore. It's too many variables that you can't control. So, but you can play with that at home if you want to. All right. I think we have time maybe just to introduce weight and mass. Okay. What we've already said, by the way, I probably haven't said this. Mass is one of those invariants. What we mean, it doesn't change. An object's mass is its mass is its mass. Velocity, that could change. Okay? Acceleration, that could change. Displacement, that could change. Mass doesn't change unless you're losing mass. Well, literally. Okay. So mass is a quantitative measure of the inertia of an object. We've already said that. The mass is related to inertia, the amount of matter that's there. Okay? Now, weight is not the same as mass. Weight is the force of gravity pulling down on the mass. So, guess what acceleration is involved with that? The acceleration due to gravity, that g that we use. 9.8 meters per second squared, 32 feet per second squared. Weight is a force, mass is just how much of it there is there. So pounds and newtons are equivalent. They're not the same, but they're measuring the same thing. Pounds measure force, newton measure force. These are measures of force. Kilogram is a measure of mass. Now, I bet you most of you have never used the U.S. customary measure for mass. I think we talked about this before, didn't we? Was it? You all remember what it was called? A slug. You're absolutely right. We don't use it. So just about everything in U.S. customary, we use pounds as if that was mass. It's not. That's a force. If you go to the grocery store and put the bananas on the scale, okay, the upper thing says how many pounds it is. The inner scale says how many kilograms it is. They're measuring different things, okay? How can they use the same scale to measure two different objects? They only differ by a constant. The acceleration due to gravity, 9.8 meters per second squared, 32 feet per second squared. That's a constant, so therefore the variation is the same. So you can just set up your scale for that. Okay. So keep in mind though, forces are not masses, and masses are not forces. Force is not an invariant. For instance, if you were to take off in a spacecraft and go to the moon, would your mass change any? No. Would your weight change? Definitely, because the moon's gravity is about 1/6 of that of the Earth. So therefore, it's a great weight loss plan is go to the moon. Okay? The trouble is when you come back, you have a loss. You gain the weight right back. Okay? So now, how are we doing on time? We got time for this. Okay? Here is the relationship. Now, there's one thing that's a little wacko about this. You have to remember. This formula here is Newton's second law formula. This is always referring to net force. Okay? That's the net force that's being acted on the object. Okay? With that mass. This formula down here is still talking about, this is weight in this case. Weight is equal mass times acceleration. This is not a net force. This is the force due to gravity. The force of gravity pulling down on something. It's not a net force. It's just one of the component forces. But what they're getting at, the forms are the same. This is measured in pounds or newtons. This is measured in pounds or newtons. This is kilograms. That's kilograms. This is meters per second squared. That's meters per second squared. So the formulas are similar in structure. It's just what they're talking about. This is net force. This is one of your component forces, the force due to gravity. But the formulas are set up exactly the same. It's only this one. And this one, whatever your acceleration is, that's your acceleration. This one is always, if you're on the surface of the Earth, which is where we spend most of our lives, right? Okay, it's 9.8 meters per second squared, or 32 feet per second squared, a constant, anywhere on the surface of the Earth. If you're on top of Mount Himalaya, or at the bottom of the Dead Sea Valley, your acceleration due to gravity is basically the same, 9.8 meters per second squared. Okay. Now, I happened to be the last time I taught this. We ended right about the same spot. We'll pick up next time with example 210 on page 44. Okay? Now, the only difference next time from what we're doing today, 2 hours of class, we've just about completed that. We'll have 2 hours of lab or whatever portion of that it takes for you to do, and then we'll have 30 minutes for the test 1. Next time, since we're not going to be through with Chapter 2, we're obviously not through with it today, so you're not going to be tested on Thursday. So next time will be 2.5 hours of class and 2 hours of lab. And when you finish lab, you'll be able to go. Okay? Today, 2 hours class, 2 hours of lab. When you finish lab, you can take your test. When you finish your test, you can go. All right? So why don't you take a little break now?
When's the next test?
When we finish Chapter 2. I don't know when that'll be. It could be we'll finish Chapter 2 next time. I'm guessing we will. So that means the next test will be next Tuesday, probably. Okay. Not before, but could be later, but I think next Tuesday. All right. So what I'm going to do is end the recording for now. All right, this is Lab 2. The title of it is Motion, mostly describing motion. We won't be explaining it too much. A little bit, maybe. Each team has 3 balls on the rack here. 1 plastic, that's the ping pong ball. 1 rubber, that's the rubber ball. And 1 metal, the metal ball. Okay, first thing you've got to do is determine the mass of these 3 balls. Okay? Now, if you can get, before you do anything, be sure you zero your scale. Don't count on the other team having done it better. And if you can get the ball to sit on here without rolling off, you can just do that. If you do need the weighing tin, you put this on and then zero the scale. Okay? So you zero the scale before you put the ball either on the scale or in the tin. Be sure your zero is going to measure the mass of the ball only. Now there's 2 scales, 3 teams share. It doesn't take long to do it. You can be doing that. Whoever's going to get started. And the grams, the scale is measured in grams. You can use that if you want to. Yeah. Okay? And what y'all can be doing is not much, but a little bit. You can take your ruler, and what you're going to do is from inside to inside. So get it to the closest 1/10 of a centimeter. And that will be on your B part of the front page. Okay. Y'all are letting him do all the work, huh?
He looks like he's having fun.
Oh, okay.
He's an expert.
Yeah.
You're going to let him have all the fun?
Yeah.
Oh, man, y'all are kind.
That's the one that makes the money.
What you do next is you do what I told them.
Sort of. Not entirely.
Okay. Zero in the scale.
No.
Right up against. Whoa! This is cool. Let me go get you another wrap. I'm sorry. I did not realize it may have actually come apart while I was bringing it up here.
So you think we
I just didn't notice it. Sorry about this.
I'm going to take you on with
I'll be back.
I used to put you in
All right. So all teams. Okay. A little bit of your meter stick. If y'all haven't done this, listen up too. Place the zero end of your meter stick up against the inside of one of the metal plates and read to the nearest tenth of a centimeter the length to the inside of that plate. Okay? Y'all got your okay, take the balls out of the way. Yeah, okay, yeah, you don't have to, but yeah. All right. That's all we're going to be using it for. Y'all got your measurement? There's a tenth of a centimeter. All right. So everybody has the mass of the three balls and the length of your track. There's a tenth of a centimeter. Okay? Now, flip over to page 2. Now, I've set all three of your scales, your inclined planes, to 5 degrees. Pretty close to it anyway. Okay? So each of them should be at 5 degrees. Now, you'll notice where you measure from is the bottom of this metal piece here. The long side, that is your angle measurement. Okay? Not the top, the bottom of that. 5 degrees. No, the bottom. I had it set. Okay. All right. That's at 5 degrees. Okay? Now, you'll notice the first 3 blocks are all at 5 degrees, so you do the 3 balls. And what you're going to do, in whichever order you want to, and here's what I suggest, I recommend. Let's just say, okay, you each have a stopwatch. Let me just explain the operation of the stopwatch. It's pretty simple. The button at around 2 o'clock, that's the start and the stop. I read that. That was 1.22 seconds. That's what you're measuring. Then reset is the 10 o'clock button. That takes it back to 0. Do not press the center button. That changes the mode, and then I've got to figure out how to get back to the right mode. So only press start, stop. That was 1.34 seconds. And reset. Okay? So what you'll do, and what I suggest, okay, is that the person who's releasing the ball also operate the stopwatch. The other record the times. Okay? Don't record it on the sheet. What I would recommend is open it up this way and maybe record your times here. Because what you're going to do is do 3 times for each ball at each elevation. Okay? So I'll just do a rough thing. Okay? When I release the ball, I'm going to start the clock. When it hits the end, I stop the clock. And then tell your teammates how many seconds. Okay? So I won't tell you how many mine have. Okay? So I suggest the person who's operating the stopwatch is releasing the ball and stopping. Okay? Do 3 times for each. Now, rather than averaging, here's what I suggest. Okay, now if those 3 times one of them comes up wacko off, like you didn't press it in time, or you let it run too long, or it didn't operate properly, do that one again. Get 3 times relatively close to each other, throw out the high and the low, take the middle time. That's what you put on the data sheet, the middle time. Do 3 times, throw out the high and the low, and record the middle time. That will be in seconds. Once you got all your times measured at all the different angles, then let me know and we'll talk about the next one.
Are we supposed to be in minutes?
These are seconds. Okay? No. Start, stop. That's 1.12 seconds. Okay? Reset. Okay? That thing is just as the LED's out. You're not going to get that high. I hope. We'll be here all night. Okay. All right. I've got to go back to the classroom and pick up a red pen so I can grade Ethan's paper.
Plastic, rubber, and what we doing first? That was for rubber.
Not just to show them. Rate acceleration is the same problem.
Any questions so far?
1.5. Yeah, 1.6. Yeah, no, 1.53.
Okay, look, I'm sorry.
No problem.
What's
that?
What was supposed to put on time?
Okay. You're doing 3 measurements for each ball, each elevation. As long as those 3 times are relatively close to each other, throw out the high, throw out the low, take the middle value.
And that'll go on time.
That'll go on the time in seconds. Everybody understood that?
What's that?
Your time is in seconds. Throw out the high and low. Do 3 times at each ball, each elevation.
That's the turn this one. You got to start to set your drive.
Just take the middle.
I'm not gonna be able to
It says average. You gotta get the 3 of them.
This the time. He said for the time you choose the middle.
Right.
But then
And that average is time.
the average right here, so the middle you have to add.
No, I'm about to say, go for
But that comes for the middle.
it.
And then I don't know if
We doing
average from the time.
Go, that 2-1. Key last. 1.16, like you said. I don't think Trent knows you can stop once you hit that way before that got there. That's more like.
until there's questions or I need to talk again, I'm going to pause this. Taking your time. Here's how we calculate the next column, which on your data sheet is named average speed. Okay? If you remember from class, the average speed, I don't know if you can read this from where you're sitting because the pen is very weak, but the average speed, V bar, is change of distance over change of time or just distance over time. The distance was what you measured from top to bottom plate. That's the distance in centimeters. The time was the middle time that you recorded for each ball at each elevation. So for your second column here, you'll take the distance you recorded on page 1, the length under B, or centimeters, to the nearest tenth of a centimeter, divide that by the time that you recorded in your first blank column. Y'all already working on that? Yep. Okay, good. So that's what you do next. Do your average speeds. I don't know if sound could pick that up, but you know what? Since Dr. Wilson cleared off the table, I'm going to move this up here. Okay, since everyone pretty much has gotten their second column filled out, average speed from right here is everybody, you don't have to put them all in, just put a few, okay? You're okay. All right. Now get people, okay. Don't want anyone to miss it. Okay. Now. Okay, yeah. All right. Since you found out your average speed here, distance over time, there is another way to figure average speed. When you have uniform acceleration, do you remember what that was? What's your average score? Add your initial to final, like you've had 2 labs, and divide by 2. Okay? Well, that's also how another way to get average speed. Don't pay attention to this 2 here. Average speed is initial speed plus final speed divided by 2. Right? Average them together. What was your initial speed? 0. You released it from rest, didn't you? So we got average speed. To get final speed, what we do is multiply both sides by 2 to wipe out your denominator here. And that's 2 times the final speed is 2 times your average speed. So what you put in the average speed column, double it and put that in the final speed. Right? Make sense? Good deal. Okay. I'm going to put... Say again? You got it. No, I just that last part. Okay. Your average acceleration then is your final speed minus initial speed divided by your time interval, which initial speed 0, final velocity column 3 divided by your change of time or your time interval, which is column 1. That's your average acceleration. Question I'd like to get, please give me an honest answer on this. Okay, when you started this, which ball did you think would be the fastest rolling down the track? The metal? What did your data show? It's what? The plastic was what? Fastest? Consistently? Really, not really. They all were probably within about the same speed for each angle, weren't they? Okay? And about the same accelerations, right? Now, if you got right near the same. So what does this show you? That last question. The angle. That's the only thing that matters, is how steep that angle was. It's the main thing that matters. Okay? Any questions? Thought the lab was worthwhile or not? Okay? Now, if you're finished with it, I'll take it. If you want it, you can have it up to a week, you know, if you need it that long. Y'all, yeah, take your time if you're not through. You've got plenty of time. What time is it? Huh? 6:30. Yeah, we go until 6:45. 7:15 for lab and 7:45 for the end. I think we're gonna make the lab done. Huh? Okay. Now, if any are ready to go and start your test, you would rather do that back in the classroom? Right here? These are not nearly as comfortable as seats. You want it here? I'm all in favor. Okay. You can have your formula and equation sheet, calculator for sure, and right there on the. I don't mean to rush y'all. Take your time. Red eye. Oh, you take your time. Okay, does anyone not get a test yet? I'm missing 3, and I'm only supposed to be missing 2. Release of that. Four, and 3. Must have miscounted. If there's no more questions, I will turn off the recording. It shouldn't have been on this long.